So, time to move to the next chapter. Chapter 16, the degenerate remnants of stars, neutron stars, white dwarfs. We know that the sun will leave behind a white dwarf supported by electron degeneracy, that more massive stars can leave behind after they blow up as a supernova a neutron star supported by neutron degeneracy pressure. So let's talk about how degeneracy pressure works in general. So, time to go back to that tried and true infinite square well from quantum mechanics, because that'll be the basis of our understanding after we make the cubical star approximation. Y'all know about the spherical cow approximation, right? So when we talk about white dwarfs and neutron stars to derive an expression for the degeneracy pressure, we're going to assume that they're cubes, because it'll be just fine. You get the right result, and it's a lot easier than trying to use the eigenfunctions that would apply to a spherical geometry. Cartesian geometry is easier. But first, let's get a reminder here. So last time I asked this, nobody could tell me. The one-dimensional time-independent Schrodinger equation, what is it? What's the one-dimensional time-independent Schrodinger equation? All right, let's see. I'm going to ask another question. So if I have a particle, what kinds of energies will a particle have? There's two kinds of energies it might have. Why, there could be kinetic energy and potential energy, right? And in terms of its momentum, if I'm just speaking classically, in terms of its momentum, what is the kinetic energy equal to? Just normal kinetic energy, yeah.
P squared over 2m.
Yeah, P squared over 2m, right? I know, 1/2 mv squared and all that, but momentum, mv, non-relativistically, is more fundamental than velocity is. And so P squared over 2m is m squared v squared over 2m, which is the same thing as 1/2 mv squared. Really, you should think, when you hear kinetic energy, the first thing that comes to your head should be P squared over 2m rather than 1/2 mv squared. It's going to now, P squared over 2m. P squared over 2m. When I say kinetic energy, you say?
P squared over 2m.
That's right, yes, P squared over 2m, okay? So a particle's energy is P squared over 2m for the kinetic energy, plus, if we're in one dimension, plus whatever the potential energy is a function of x, is equal to the particle's total energy. And if you had me for 280, then we talked about what the momentum operator is, because what I want you to be able to do is just, you should remember the one-dimensional Schrodinger, time-independent Schrodinger equation, because it's just operator substitution. And so it's not something you really need to memorize. If you just remember P squared over 2m plus v equals e, you can easily get the Schrodinger equation, because if you remember the momentum operator, and I'm just going to call it P, sometimes we put like a hat on it to say it's the operator, or a P sub op, but no, I'm just going to call it P, the momentum operator. Anybody remember, what is the momentum operator? It has a derivative in it. And it's quantum mechanics, so what else should it have in there? So yes, so it's got ddx, but it's not psi, it's an operator. So it's waiting to attack a wave function. No, so psi is not part of the operator. The operator, like the derivative operator ddx, is just that, waiting to sneak up on some unsuspecting function and differentiate it. But the operator itself is just the ddx, but the momentum operator's got a couple things in front of that. It's quantum mechanics, so therefore some constants just got to be there. Who's some really important kind of quantum mechanics guy that just shows up everywhere? Yes, h bar is going to be in there, right? Planck. And then Well, let's not try to get too real about this. What else might be in there? Ay, can you remember? I, yeah, it's minus IH bar. ddx is the momentum operator. And so therefore, p squared, the operator for momentum squared, will be, for a function, you would hit it twice with minus IH bar ddx. And so if you hit it twice with minus IH bar ddx, that's doing this to the function. You take minus IH bar ddx of minus IH bar ddx of whatever function you put there. So let's see, I've got minus I times minus I is what? It's minus 1, right? That's going to be minus 1 because I, no, wait a minute, yeah, minus I times minus I, yeah, minus 1, yes, very good, me, yes, right, because minus minus, well, that cancels out, and then I squared, of course, is minus 1, and then what's H bar times H bar? H bar squared, right, and what's ddx of ddx? D squared dx squared, right? So minus H bar squared d squared dx squared is the momentum operator squared, and the Schrodinger equation is just an operator version of p squared over 2m plus v of x equals E. In other words, we just turn that thing into operator equation and hit psi with it. And this is just the number, so as an operator, it's also just that number, whatever the energy is. And V of x, now this is getting fancy, in the momentum basis, the potential energy operator is simply, sorry, in the position basis, I meant to say. In the position basis, the x operator is just represented by multiplication by x, and any function of the x operator is just that as a function of x in what we call the x basis. So in other words, we just write p squared over 2m psi of x plus v of x psi of x equals E times psi of x, where it's understood that's the operator, p squared over 2m, that should show up there. This is the general prescription for quantizing a system, is you write down the classical equation that describes the system, promote everything to operators, and then apply them to the wave function. This is how you come up with the Schrodinger equation that describes the system. So the operator p squared is minus h bar squared d squared dx squared. So this says minus h bar squared over 2m. And then because we don't have any time dependence here, because x is the only variable, the partial derivative with respect to x is also the total derivative with respect to x. And so I can just say d squared psi dx squared plus v of x psi of x is equal to E psi of x. And there it is. That is the one-dimensional time independent, because we didn't put any time dependence in there, time independent Schrodinger equation. And as Dr. Trees likes to abbreviate it, and I've just picked that up as well, right, that's TIES, time-independent Schrodinger equation, TIES. I like to call the Schrodinger equation in general. What do I like to call the Schrodinger equation in general, since I like cartoons or computer animations, or it's Shrek, right? I like to say Shrek, S-C-H-R-E-Q. So here's TIES. It's the time-independent version of Shrek. So why you should you just want to be, you just know what the time-independent Schrodinger equation is. And if you forgot, well, if you remember p squared over 2m plus v is equal to e, and you remember minus IH bar d dx, you can come up with that. So there it is right there. Isn't it beautiful? Isn't it glorious? There it is right there. Questions, comments, observations. This is review. But I want you to follow along with what we're doing, and I want to, reinforcement is the key to learning. You want to just know that cold, basically, or at least be able to quickly come up with that. Remember that the momentum operator is minus IH bar d dx. So if you've had QM with me, you'll certainly know that not everybody at the 280 level talks about the operator like that, but I can't help myself. You got to have the operators in there. It's just so fundamental and fun, So, alrighty. And then why we always like to go to the infinite square well, because it's kind of the simplest non-trivial quantum system that you can solve. And so we like to draw it like that, right? This is the infinite square well, also called the particle in a box. And I like to sometimes do that because that's quicker to write than infinite square well there. That's the infinite square well, particle in a box. And the reason I'm going to do this is because we're going to treat the electrons in our white dwarf as being in a cubical box that represents the star, if you will. And we're going to assume that they don't interact with one another. Even though they actually repel one another electrically, it's much easier to treat it assuming that they don't have any interaction energy. And again, we get essentially the right result. But the professionals have to put in the interaction if you really want to get everything right. But we'll get essentially what we need by just treating them as particles that do not interact. Got the infinite square well, so that's where if I say here's the x-axis and that's x equals 0 and that's x equals L, then we say the potential energy is equal to 0 for 0 is less than x is less than L. Inside the well, the potential energy is 0. And what do we say the potential energy is outside the well, everywhere else? It's the infinite square well. What do we say the potential energy is everywhere else? Infinity. Infinity, yes, infinity. Everywhere else. So we represent that as just two spikes that point up to infinity, but it's understood it's the potential energy is infinite everywhere else and 0 inside the well, and that has the effect of confining the particle to the box. It's absolutely impossible for it to get outside of the box. So we call it the particle in the box because the classical analogy to it would be a particle is in this, again, we're only in one dimension right now, but in one dimension, it's in a box that it can't get out of. So the classical system, if the particle had a certain amount of kinetic energy, would the kinetic energy be changing as it moved inside the box if it were a classical particle? Would the kinetic energy be changing? Well, would the total energy be changing? No. And is the potential energy changing as it moves around? No, because the potential energy is 0 everywhere. So does the kinetic energy change as it moves around? No. So what does a classical particle do here? I'll be a classical particle in a box. The infinite potential energy represents this idea that you've got these spikes here, can't get outside. What are you going to do at the boundaries? Yeah, right? Hi, I'm a particle in the box defined by these two walls. Here I am with constant kinetic energy. Ah, it sure is fun to sail here. And right? Oh, here I am going backwards with the same kinetic energy I had before. Yep, my energy's staying constant. Oh, here I am with that same. So this is a really fascinating problem. It just does this forever and ever and ever, right? Back and forth, just forever and ever and ever. But this is quantum mechanics, and so we've got a wave function. In quantum mechanics, which means in the real world, do particles really move with well-defined positions and velocities and all that well-defined? No, they don't. And so we can talk about energy eigenstates. A particle doesn't have to be in an energy eigenstate. It can be a wave packet that describes it. In fact, that's generally going to be the case. But we can find the eigenfunctions and eigenvalues. In other words, the wave functions that have definite amounts of energy in here. So, Shrek in the box. Oh, you got Jack in the box, and now we got Shrek in the box, right? You open it up, and it's like, a green thing with a Scottish accent comes out and starts saying hello to you, right? Okay, Shrek in the box. That's going to be minus h bar squared over 2m d squared psi dx squared plus v psi. What's v inside the box? 0, so we don't have that term, equals E psi, right? Minus h bar squared over 2m d squared psi dx squared is equal to E psi. So why not just turn this into d squared psi dx squared is equal to minus 2me over h bar squared psi. Why not call all that stuff together k squared and just say d squared psi dx squared is equal to minus k squared psi, where k squared, by definition, is equal to 2me over h bar squared. Sounding familiar? I think you've seen this before, right? You've dealt with this beastie before. So, what else do we need to figure out what psi is? Because there is a solution for every energy. You tell me an energy, and I will give you a solution of this equation that has that energy. But is every energy allowed inside the box? No, why not? What is it that we also have to impose on our solutions? Boundary conditions, right. It's the boundary conditions that put the quantum into quantum mechanics. It's because of boundary conditions that we have quantization, so we have to impose boundary conditions. It's a misconception to think that the Schrödinger equation produces quantization of energy. No, not by itself. Boundary conditions are responsible. Impose boundary conditions. What are the boundary conditions on the wave function? Do you remember? Or what are, actually I'll put it like this. Okay. So in general, I'll say, right, because this is going to show up as a boundary condition, but in general, psi must satisfy that at each value of x, it is, I'm going to start spelling it, and then you're going to try to jump in and complete it as quickly as you can. It is C. Oh,
Constant?
no. Although there's an n, it's not constant because if psi were constant everywhere, that would be like psi itself. Yeah, it's continuous. Bing, 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 bing. Bing, bing, bing. Psi has to be continuous. And generally, d psi dx is, yeah, continuous. But there's an exception. And these come from a consideration of the Schrodinger equation itself, these two conditions. Psi, well, I'm not going to go into that here. Psi need not be continuous at values of x where v of x has an infinite discontinuity. So in most of the time, psi and its derivative have to be continuous everywhere. But if there's an infinite discontinuity in the potential energy, V of x, then d psi dx doesn't have to be continuous, but psi still does. In the problem at hand, can you find any locations where there's an infinite discontinuity in the potential energy? X equals 0 and x equals L. So we're in precisely a situation where there's a pair of points where there's an infinite discontinuity in the potential energy. So this happens at x equals 0 and x equals L for the infinite square well. If I really wanted to get, but then it would not be speeding up things. I could draw like a little well with a bucket and stuff like that, right? But, right? Yeah, maybe it's like okay, here's my well. Let's see. So there's my thing, and here is my bucket in the well. Oh, look, it's an infinite square well. Okay, that get a little slow to keep drawing all the time, but I kind of like it. I never thought of that before. Wow. Okay. So if you can draw very quickly and you want to make that the new symbol for the infinite square well, you go ahead. But anyway. This happens at x equals 0 and x equals L for the infinite square well. So we just need psi to be continuous everywhere. Yeah. This is going to be great for your reading pleasure, Kathleen. Everywhere in the well, including the edges. And now finally the boundary condition. The BCs here are that what happens to psi at the boundaries? Not only is it's got to be continuous with psi outside there. What is psi equal to at x equals 0 and at x equals L? Which really, we're just kind of hand waving this or chicken feet waving it. You can get it by considering the finite square well and taking the limit as the height of the barrier goes to infinity. But do you remember, what is the boundary condition on psi for our infinite square well here? Psi at the edges, x equals 0 and x equals, well, what is psi equal to there? It's 0 on the edges. We argue that, well, if the particle could get, if it wasn't 0 there, it'd have like infinite potential energy. You'd have a finite chance of finding it with infinite potential energy, and that doesn't seem good. And that's not a rigorous argument, but again, you can solve the finite square well, take the limit as the height of the barrier goes to infinity, and you find psi goes to 0 in that limit. So we're just going to make the assertion. BC's here are that psi equals 0 at x equals 0 and x equals L, right? The edges of the well. Psi vanishes on the boundaries. That's our boundary conditions here. And it's 0 outside, too. So in other words, if I were plotting psi outside the well, psi is 0. Psi is 0. When x is less than 0 and when x is greater than 0, psi is equal to 0. But we don't want it to be 0 inside the well, because is anybody home if psi is 0 everywhere? No, there's no particle there. So that's a solution, but it's not a very interesting solution. So we need solutions. We need solutions of d squared psi dx squared equals minus k squared psi that vanish or equal to 0 at x equals 0 and x equals L. Those will be solutions of the time-independent Schrodinger equation, and that'll tell us the solutions that have definite energy, that are energy eigenstates. So, did you get it?
Yeah, I read as so lines.
What's that?
I read solutions as so lines.
Oh, so lines. Oh, I see. Oh, yeah. No, solns. Solutions of, right. Yep. Okay. So what is the function whose second derivative is minus k squared times the function itself? What are some functions? There's two linearly independent solutions of d squared psi dx squared is equal to minus k squared psi, that the second derivative is minus k squared times the function itself.
Sine and cosine.
Sine and cosine do this, right? Getting tricky with it, right? Sine and cosine do this. So sine what will have its second derivative be minus k squared times the function itself?
Kx.
Sine kx does the trick. Sine kx, and what's the other Li solution if we start with sine?
Cosine.
Cosine also has that property. Sine kx and cosine kx solve our solutions, our solines of d squared psi dx squared is equal to minus k squared psi. Just as a reminder, like for example, d dx of sine kx, if I take one derivative, what's the derivative of sine kx? K cosine kx, right? K cosine kx. And if I take then the second derivative, d squared dx squared of sine kx, well, that's d dx of k cos kx. When I take the derivative of k cosine kx, what do I get? Yeah, so, right, that's what I'll get, right? When I take cosine kx's derivative, that's minus k sine kx, and there's already a k hanging out there, right? So the second derivative of sine kx is minus k squared sine kx. So in other words, that works. If you said psi was sine kx, its second derivative would be minus k squared times psi, right? And if you put in cosine, the same thing will happen. The first derivative of cosine kx is minus k sine kx, and the derivative of the second derivative then will be minus k squared cosine kx. So they both work. So that means that any linear combination of those two linearly independent solutions of our second order ordinary differential equation will be the general solution, right? Remember that from ODEs, if you've taken ODEs, right? The glories of all of that. It's almost like things you want to learn in one class can be applied in other classes. You know, isn't that weird? So we can write down then our general solution. And again, this you've seen this before, but I didn't want to assume that you remember it or that you couldn't possibly benefit from a review. And the reason is because I'm right. you can benefit from a review, I'm guessing. So general solution. General solution, okay? Salute our general solution here. General solution, psi of x is a sine kx plus b cosine kx. And again, any value of k works. There's no restriction so far on the values of k and therefore on the energies. I can solve the Schrodinger equation inside the well for any value of the energy, but it's not good enough just to have a solution of the Schrodinger equation, because that solution must also satisfy the boundary conditions that are going to put the quantum into quantum mechanics, right? So the BC at x equals 0 says psi of 0, which will be a sine k times 0 plus b cosine k times 0 is equal to what? Psi of 0 is equal to 0, yeah, is equal to 0. What's sine k 0? What's the sine of 0?
Sorry,
That's 0. What's the cosine of 0? 1, right? So this says b equals 0. That's what we get out of that boundary condition. b equals 0. b has to be 0. Otherwise, our function would be being obnoxious and like not being equal to 0 on that boundary, but it's not allowed to not be 0 on that boundary. So b has to be 0. So now we know that psi of x is equal to a sine kx. It has to be a sinusoid in there. No cosines allowed. Get out of here, you filthy cosines. Okay, here we go. Here's a sinusoid. Did it work? Nope. It's the solution of the Schrodinger equation, but it didn't work. Why didn't it work? What's wrong with this solution? That's going to be 0 on the other side too, so we have to impose the second boundary condition now. Psi equals 0 at x equals L now says a sine k what equals 0? Sine k L, because if we're putting in x equals L, a sine k L is equal to 0. So notice any value of A works. So we just have sine KL is 0. The A is not really playing a role here. So this is a condition on the value of K times L. Where is the sine function equal to 0? For what values of the argument is sine equal to 0?
Some integer times pi.
Yeah, any integer times pi, right? So we could say 0 plus minus pi plus minus 2 pi, da 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 da. If we let KL be 0, this is not terribly interesting because that would say K was equal to 0 because L is not 0. And if K was equal to 0, it's a solution, but why is it not an interesting solution?
Not making the energy 0.
Even more so, what would psi be everywhere if K were 0? It'd be just 0 everywhere, right? And if the wave function is 0 everywhere, is anybody there? No, there's no particle there, right? So we toss that. No particle, that's a boring solution, right? Well, I've solved the Schrodinger equation in the well by simply refusing to put a particle there. That made my experiment so much easier because I was able to go home calling myself finished. And you get an F on your lab report. Not that you can put particles in it, whatever. You know what I'm getting at, right? Okay. And then meanwhile, we can choose K to be positive because in the end, how do we actually find probability in quantum mechanics? Does the wave function directly tell us probability, or do we have to do something to it first? How do you, what's that? Well, yeah, you do have to do something, yes. What do you have to do to the wave function to find the probability density?
Multiply by itself.
Yeah, almost. You multiply it. If it's real, you multiply it by itself, but if it's not real, in general it isn't, you would multiply it by its complex conjugate. You'd multiply it by its complex conjugate, right? And well, here you can choose in the one-dimensional, you can choose the time-independent wave function to be real here. And so you just square it, literally. So is it going to care whether psi is positive or negative? Multiplying by -1 on psi doesn't change anything physical because psi squared would still be the same either way. And so a solution with KL being pi would just be minus solution of KL being minus pi because sine of minus theta is minus sine of theta. So in other words, if we allowed negative values here, we would just get -1 of the wave functions with the positive values. So we are free to restrict K to be positive because negative values just multiply the wave function by -1 and don't change anything. If we were weird, we could say, all right, if I want every third one to be positive and all the rest of them should be negative, you could do that, but then there'd be something wrong with you. So we can choose K to be positive since K less than 0 just multiplies the K greater than 0 solution by -1, and that's nothing new. So in other words, we can then say that KL is equal to pi, 2 pi, 3 pi, blah, 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 blah. Or in other words, KL is equal to n pi, n equals 1, 2, 3, blah, 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 is how we usually say it. K is a positive integer, KL is a positive integer multiple of pi, because those are the values where sine of KL will be equal to 0. Or in other words, K sub n, give it a subscript to label it, K sub n is equal to n pi over L, n equals 1, 2, 3, dot, 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 dot. And then we say, okay, psi sub n of x is a, we could say sub n sine of n pi x over L. And n is equal to 1, 2, 3, blah, 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 blah. And this is where you can see, right? If I replaced n with minus n, the sine of minus n pi x over L is minus the sine of n pi x over L, right? In other words, the sine of minus theta is equal to what? Sine of minus theta is minus sine theta. Minus sine theta, right? That's a property of the sine function. It's anti-symmetric about the origin. So the reason I don't bother with negative values of n is because they would simply be minus versions of what you get for positive values of n, and that won't make any difference because it's only the probability that you can directly measure. And so multiplying the wave function by -1 doesn't change anything physical. So those, again, we could decide, oh, we'll always choose n to be less than 0. Or if n is even, we'll call it positive, and if n is odd, we'll make it negative. Or every thousandth value of n will make negative. The other ones we put, you could do something weird like that. Who would do that? You just pick positive values for n, for all of them. Even though you could do any other combination you like, it's just don't duplicate anything. Don't have any plus and minus values of the same n. Okay, what questions do you have? Because what we're going to do is move this into the 3 dimensions in order to look at what happens inside of a white dwarf and a neutron star. And then in a homework, the next homework, you will delightfully look what would happen if you had a 2-dimensional version of this. So we'll do the 3-dimensional version, and for kicks, you'll figure out, well, what if you had a 2-dimensional white dwarf? What would be the pressure inside the 2-dimensional white dwarf, and so on and so forth? Just for kicks. There aren't any, but you could imagine white dwarfs in flatland or something like that. Okay, and the math is fun. All right, so, and then how do you figure out what the value of a sub n is? We're actually not going to care about it, but what would I do? What sets the value of a sub n? There's this other thing we need in quantum mechanics. What's that? So right, so how would we decide what to make a sub n equal to? So remember that the probability density, in other words, the probability of finding the particle in a little range dx, x to x plus dx, is the absolute square of the wave function, dx. Now, this is a real one, so it'd just be ordinary psi squared, but that's also the absolute square for a real function. For a real number, its absolute square is its square, because what's the complex conjugate of 7? 7. What's the complex conjugate of minus 46? Minus 46, right. For a real number, the complex conjugate is just the number. So psi star psi is psi squared for a real function psi. But just to be general, we can just say, it's the absolute square of psi dx, right? Okay, so the probability of finding the particle between A and B, the probability that you'll find the particle somewhere between A and B, what would I write for this? It'd be the integral from A to B of, I should have not, here, pretend I didn't write the limits, right? So P of x dx, probability of finding a little dx is psi squared dx. So in general, I have to integrate the probability density psi squared dx. When if I want to find it between A and B, what are my limits of my integral? A and B, I would integrate from A to B, right? So if I just had some general wave function, if this was like psi squared, if that's psi squared, then if this is A and B right here, that integral, psi squared dx from A to B, that area under the curve of psi squared would be the probability of finding the particle between A and B. So what is my, what's the magic word I'm looking for here? I'm looking for an n condition. The wave function needs to be n. What is it? What's the probability I'll find the particle somewhere between minus infinity and plus infinity? It is 1, right? Because it's got to be somewhere, right? So the idea that I have to find the particle somewhere, the probability I'll find it somewhere between minus infinity and infinity, well, that'll be the integral. What integral am I writing down here? What are the limits? Minus infinity to infinity of what's my integrand in general?
Absolute value is 7x squared.
Yeah, psi, the absolute square of psi. You don't want to say absolute value because it's not right. The absolute square of psi dx. And what's that need to be? 1, right? And this is called what condition that starts with an n?
Normalization.
Yeah, normalization. This is the normalization condition. Psi has to be normalized. And this is how you figure out that constant out in front of the wave function. That's how you figure out, right? In other words, any multiple of psi is still a solution of the Schrodinger equation that satisfies the boundary conditions, but not only does psi have to satisfy the boundary conditions, it should be normalized as well. And that's what will tell you what the constant that's left over after you've done everything else needs to be set equal to. So in this case, how would I find a sub n? What would I write down? What integral do I write down to find what a sub n is over there?
0 to L.
Yeah. Why 0 to L? Why not minus infinity to infinity?
They can't be outside.
Can't be outside the well. Psi is 0 outside the well. So I could write minus infinity to infinity, but psi is 0 outside the well, so that all that matters is inside the well, 0 to L of absolute square of a sub n, because a sub n, you could make it complex if you were fond of making it complex. Absolute square of a sub n times what? What else is there? I'm finding the absolute square of psi. Psi is a sub n psi n pi x over L, so what's the absolute square of psi? It's going to be absolute square of a n times sine squared. Yes, psi star psi, right? If this is psi, what is psi star? Sine star of x. If psi is a n sine n pi x over L, what's psi star?
The complex conjugate of a n times sine.
Yep. A n star sine of n pi x over L, because the sine function is real, so it's its own complex conjugate. I can make a sub n real, in which case psi n star would also just be a n, it would be psi again, a n's sine n pi x over L. But I don't have to make a n real. So in general, it could be complex if I'm a little weird and I wanted it to be complex. And actually, you may want, so if you have a linear combination of wave functions, you may well need the coefficients to, in general, be complex. But if I'm just looking at one eigenfunction like this, I don't have to, but I'll be general. This is the integral you would do to figure out what a sub n is. And if I recall correctly, what you find is that if you want a sub n to be real, it's root 2 over L, if I'm not mistaken. I think it works out to be root of 2 over, square root of 2 over L. I have to look it up, but that's my best memory. Which could be multiplied by an arbitrary phase, e to the I phi, because when you take a n star, you'd get an e to the minus I phi, and that would kill the e to the I phi, so everything would be cool. But if we could just choose it to be real, and I believe it works out to be root 2 over L. So if you need it, then that's how you find out what a sub n is, is to normalize. You do that integral and solve for a, because sine squared n pi x over L, you could just write down what that integral is and go from there. So anyway, okay, what questions do you have? Is this ringing a bell? You've seen this before? Ah, such delightful memories, right? Seeing it all again. I love this stuff. I do, actually. So after our break, we'll kick it up to the third dimension. Mention. All right, so if we wanted to sketch what the wave functions look like, right, then we know that k sub n is n pi over L, and so we know that they are sinusoids that vanish on both ends of the well. So if I wanted lambda sub n, how would that be related to k sub n? How are k and lambda related when we talk about, like, you know, sine kx? What would be the wavelength associated with that? Stand on your head and say it again. 2 pi over k. The wavelength is 2 pi over k. So lambda sub n is 2 pi over k sub n. So that would be 2 pi over n pi over L. So that would be what? That'd be 2 pi times L over n pi. So that would be lambda's, what am I doing here? I don't like this. It's supposed to be, no, I'm fine. Yeah, okay. So this would be 2L over n is lambda sub n. And then I think a better way to put it is that L is n times lambda sub n over 2. Or in other words, and this would be n equals 1, 2, 3, blah, 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 blah. In other words, an integer number of half wavelengths fits inside the box. An integer number of half wavelengths fits inside the box. Right? Because the length of the box L is an integer times half a wavelength, lambda sub n over 2. And so it's just like waves on a string where the string is tied on both ends, and what do the normal modes look like, right? So if n equals 1, what do I sketch for the wave function there? It's a sinusoid. And if n equals 1, half a wavelength fits inside the box. What does that look like? Yeah, it's the one hump thingy, right? So it's like, in other words, I draw one hump, so to speak, there. One antinode in between. So this is n equals 1. So this would be like psi sub 1. And I'll just continue over here, because why not? That's when one half wavelength fits inside the box. And if I have width of its L, if I have two half wavelengths fitting inside the box, what's that look like? Right, yeah, so that's one wavelength fits in, so that's psi sub 2. And if I wanted psi sub 3, and these are all the same width, even if I don't draw them the same width. If 3 half wavelengths fits inside the box, how does your finger sketch that? Yeah, right? So that's the n equals 3. Etc. Right? So just have more and more half wavelengths in there. And then we said that k squared was 2me over h bar squared. So that says that E is h bar squared k squared over 2m. And notice that looks a lot like P is h bar k, P squared over 2m for the energy, because it's all kinetic energy inside the box, if you will, as an aside. So E is h bar squared k squared over 2m. There's an L in there somewhere, isn't there? Yeah, no, that's fine. Yeah, h bar squared k squared over 2m. But K, I'm losing it here. K is, K sub n is n pi over L. So I could say E sub n is h bar squared k sub n squared over 2m. So that'll be h bar squared, I'm losing it, let's see, n squared pi squared over 2ml squared. N squared h bar squared pi squared over 2m L squared are the energies. I think I did that right. Did I do that right? You're like, oh no. Yeah, I did. Yeah, because Kn was, right, this is sine k sub nx, so Kn is n pi over L. So Kn squared is n squared pi squared over L squared. So h bar squared k squared over 2m is n squared h bar squared pi squared. Actually, I'm going to make it pi squared h bar squared, just to put the h bar last. N squared pi squared h bar squared over 2ml squared are the energies inside the well. So what's the ground state energy? First of all, what do I mean by the ground state energy? The lowest possible energy, right? Because if you think of like your potential energy, you can't get past the ground. That's your lowest energy. That's why we call it the ground state, is in analogy with that. So the ground state energy would be, what value of n? 1. So the ground state energy is E1 equals pi squared h bar squared over 2m L squared, right? That's the ground state energy. And that lets me write all the other energies as E sub n is what in terms of E sub 1? E sub 1 is pi squared h bar squared over 2m L squared. E sub n is n squared pi squared h bar squared over 2m L squared. So E sub n is n squared times E1. Yeah, n squared times E1. So I draw a trapezoid around it because it was a little misaligned. It's a trapezoid-worthy pair of equations there. Okay. So if I wanted to draw an energy level diagram, there's E1, which is pi squared h bar squared over 2m L squared. And if I say, okay, here is 0, right? And sometimes we even pretend we're kind of drawing them inside the well, even though they're not really living inside the well per se. But how much bigger, how much taller is E2 than E1? If this is 0 for the energy, E1 is pi squared h bar squared over 2m L squared. E2 is what times E1? 4. So I have to go, okay, I should make this closer because I'm going to run out of room. Okay, so there's E equals 0. Can the particle have E equals 0? No, because that's not one of the allowed energies, which can be understood in terms of the uncertainty principle, because if the particle had energy 0, then what would you know about its speed, so to speak? If it had energy 0, what's its kinetic energy? So what would its momentum be? 0. So you would know its momentum perfectly. What's the uncertainty principle say if you know the momentum perfectly? That you know nothing about where it is, but you know it's inside the box. That's not allowed. You can't have that situation. So the uncertainty principle says you can't have energy 0, because for energy 0, you would know the momentum is 0, but that would imply from the uncertainty principle you know nothing about the position, but you do. You know it's inside the well. Not allowed. That's an aside. It's not essential to our development, but again, reinforcement is the key to learning. So E2, I'd have to draw 2, 3, 4. Here's E2 up here. E2 equals 4E1. Where do I draw E3? How many times higher than E1 is E3? 9, because it's 3 squared. So 4, 8, 9. E3 equals 9E1. Where do I draw E4? 16 times higher. I can't reach it, but it's up there, right, etc. Right, so you could just keep going. Is there any limit to this? According to the math, is there any limit to this? No, because it's the infinite square well. Now, good luck making an actual infinite square well, but mathematically, the infinite square well, why the energy could go up to infinity, but then eventually you'd be like, well, wait, I need relativistic quantum mechanics now, but shut up, you know, it's just according to what we're doing here. This is how it would work, okay? Okay, so as a prelude to what we're about to do, when we jump into 3 dimensions and throw electrons in there, imagine we're putting particles in the box. So I drop a particle into the box, I drop an electron into the box, and I want it to have as small an energy as it possibly can. What energy will it have? If I drop 1 electron into that box, and I want it to have the smallest possible energy it could possibly have inside that box, what's its wave function?
It's momentum.
No, I just want, what is the wave function that the electron will have? Will it be psi 1, psi 2, psi 3, psi 604, psi sub 604, psi sub 1, right? If I put 1 electron in there, drop in 1 electron, it'll be an energy level E sub 1. So I can represent that with a dot, so to speak, right? So drop cute little electrons into the box and minimize their energy. I want them to have as little energy as possible. Minimize their energies. So, use a dot to represent an electron with a given psi sub n. And E minus with a given wave function. Oh, I'm making Kathleen happy here. Wave function psi sub n. Use a dot to represent an electron E minus with a given wave function psi sub n. Psi sub n. Yes. Boy, you know, just because I'm writing illegibly, you can't read it. I mean, geez. Oh, wait, illegible means not readable. Never mind. My bad. Okay. All right. So with 1 electron in the box, the smallest possible energy, put it in the ground state. Drop another electron in. Where does it go if I'm minimizing the energy? A trick question is coming. Where does it go if I'm minimizing the energy? No. E1, right? Because what am I getting at here? Electrons have what spin? Do you remember? They're spin 1/2 particles, right? H bar over 2. They're spin 1/2, right? And according to somebody's exclusion principle, right? Pauli's exclusion principle, at most 2 fermions, like an electron, can fit with a fit, so to speak, can occupy a given spatial orbital, right? So if we call the wave functions orbitals, that only 2 fermions can have the same spatial wave function, but they have to have opposite spins. Stop it. Opposite spins, right? They have to have opposite spins. So our second cute little electron comes in, and it can also go in the ground state. And we're going to assume they're non-interacting, that's not true. Electrons do feel their charge, right? They'd be electrically repelling one another. If we wanted to get fancy, we'd have to add an interaction term to the Hamiltonian, right? This more complicated Schrodinger equation, and solve that. Ouch. There's, you know, and yeah, if you do it right, you have to do it. But we're not going to do that here. We're getting the big picture here. So we assume non-interacting particles. We assume they don't have any electrostatic potential energy. So that would mean, like, make the well big enough so that they, quote unquote, don't spend that much time close to one another. Most of their energy is kinetic, only a little bit is potential from their electrostatic interaction. So what's the total energy in this case if they're not interacting? Yeah, 2E1, right? Because each one has energy E1, right? So if I put in so number of electrons, and here I'm going to say total energy. And this will be in the system ground state, not the individual particles ground state, but in the system ground state. In other words, where I've made the total system of electrons have as little energy as possible, because that's an important part of where this is headed. So if there's one electron in there, the total energy is E1, because it's in the ground state energy. If I put 2 electrons in there, the total energy is 2E1. 2E1. I put a 3rd electron in there. Where's it go? E2, because can it go into E1? Nope. So it goes into E2. So what's the total energy now? Yeah, okay, you're right. Yeah, so you're right. Yeah, 2E1 plus E2, which is, I guess it's 6E1, right? Because E2 is 4E1, so it's 6E1, right? In this case. Right, because this is 2E1 plus 4E1, 6E1, right? I put in a 4th electron. Where's it go? It goes into E2 as well. And so the total energy is 2E1 plus 2E2. Uh-oh, what are we up to? 10E1. 10E1. Right? Uh-oh, I'm going to put in a 5th electron. Where's it go? E3. Do you see a pattern here? Yeah, uh-huh. Electron number 5 goes in. 2E1 plus 2E2 plus E3. E3 was 9E1, so we're up to 19E1, etc. So when we drop particles into the box, it's like an atom, right? Why is there a periodic table? If it weren't for the Pauli exclusion principle, where would electrons go in every atom? What orbital would electrons be in every atom if it weren't for the Pauli exclusion principle when it was in its ground state, its lowest possible energy? They'd be in the 1s orbital. They'd all be in the 1s orbital, and there wouldn't be any chemistry, right? Chemistry happens because of electrons having to be in higher orbitals where they do all the business of sharing and all that kind of good stuff. So thank you, Pauli exclusion principle, for allowing this conversation, because without chemistry, there aren't people talking about the Pauli exclusion principle, right? So the Pauli exclusion principle forces electrons in atoms to have higher energies than they would without it, because without it, they could all just crowd into the ground state. Okay? So, the same thing is happening in our one-dimensional box. The Pauli exclusion principle, when we add a bunch of particles in there, is forcing them to be not all crowding into the ground state level, but at higher and higher energy levels. Okay, that's important point number 1, right? The Pauli, I should probably write this down, right? Just to be right. So, the Pauli exclusion principle forces electrons in a box, because that's what we're interested for now. Later it'll do the same thing to neutrons in a box. Forces electrons in a box to have higher energies than the ground state orbital and the ground state orbital. Most of them, right? There's two down there, cute little guys, but most of them, they're up at higher orbitals. Even at T equals 0 Kelvin. T equals 0 Kelvin would correspond to the electrons having the smallest possible energy they could. Even at T equals 0 Kelvin, where they will be configured as the overall system ground state. I.e. the overall system, lowest possible energy. In other words, the Pauli exclusion principle, I put a bunch of electrons in the well, even at T equals 0 Kelvin, almost all the electrons are up at high energies because the lower ones are occupied. The analogy I like to use when try explaining the Pauli exclusion principle in Astronomy 111 and totally explaining what's going on. It's hard, but the analogy I like to use is like in a sports stadium. If you let everybody just go in and grab whatever seat they wanted, they'd probably all, there'd be exceptions, but let's pretend everybody wants to sit as close to the action as possible. Everybody wants to sit as close to the action as possible. On the other hand, you can't put everybody in the seats in the front row. You can't, right? They're already occupied. So most people get forced to sit far away from the field because the closer seats are already occupied. Similarly here, all the electrons would like, quote unquote, to be in the ground state. If they were there by themselves, they would finally end up in the ground state, but it's already occupied. And so most of them are forced into these high energy states. And the electrons in this box would be a gas because they're free particles that are doing the quantum version of bouncing around in there, exerting pressure on the walls. So even at 0 Kelvin, there would be substantial pressure because most of the electrons would be forced to be moving around quickly. So even at 0 Kelvin, there's a lot of pressure. That's kind of important fact number one, because that's going to translate directly to our white dwarf. Even at 0 Kelvin, electron degeneracy pressure will be massive, not mass, not kilograms, but large in the white dwarf, because the Pauli exclusion principle is forcing most of the electrons to be moving much faster than they would based on what the temperature would be from a classical standpoint. Even at 0 Kelvin, there's a lot of pressure because they can't all just sit down in the ground state. They're moving fast, exerting a lot of pressure, right? Because if you think like, why is there pressure on the walls of the room? It's molecules bouncing, right? And if, so my hands are molecules. I'm transferring momentum to the door. Little air molecules are going pew, 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 bouncing off of it at thousands of miles an hour, right? Bouncing off the door and transferring momentum to it, so they're exerting pressure. You turn up the heat, what happens to the speed of the air molecules? It increases, so you go from qualitatively to more pressure, right? Okay? Now, consider this piece of metal right here, right? There's what we call the crystal lattice, the metal atom nuclei. And I don't know if you know this, but you're about to if you didn't already. In a metal, the reason it's an electrical conductor is because in a metal, when you create the crystal lattice of the metal atoms, the inner shell electrons still act like they belong to individual nuclei. They're stuck on individual nuclei. But when the outer shell orbitals overlap with one another, they occupy the space of the metal, and the electrons no longer act like they belong to individual nuclei. You get what's called a conduction band, a band of energies where the electrons are free to move throughout the metal in those orbitals. They're not attached to individual nuclei. So the outer shell electrons in a metal are literally a gas of electrons. Unless you think that electron degeneracy pressure is this exotic phenomenon that only applies in things like white dwarfs and neutron stars, electron degeneracy pressure is why this is stiff. The stiffness of a metal is because of the electron degeneracy pressure of the conduction band electrons in it. And why are they exerting a lot of pressure? Well, if you calculate from the temperature of this room, kT, a typical thermal energy that you would expect classical particles to have, that is much smaller than the Pauli exclusion principle enforced quantum energies of those electrons in the conduction band. They're forced to much higher energies than they would have if you just allowed classical thermodynamics kT to dictate what their typical energy was. If you translate the typical kinetic energies of the electrons in this into a kT, calculate, like kT is like, 3 halves kT is equal to the average thermokinetic energy. If you use that to estimate the kinetic energies, the actual kinetic energies they have corresponds to a classical temperature for this of about 100,000 Kelvin. It's not 100,000 Kelvin. If it were, this would not be a good idea for me. But the electrons in here are moving at speeds that you would expect if they were a classical gas if the temperature was around 100,000 Kelvin. They would exert a lot more pressure classically at 100,000 Kelvin than they would at room temperature. Quantum mechanically, they do exert that pressure because they're moving around with as much momentum as they would classically at a temperature of around 100,000 Kelvin. So this is so stiff because of electron degeneracy pressure. Fill a star with electrons, and you can get a white dwarf where that electron degeneracy pressure is able to support the star against its own gravity without collapsing in an eternal stalemate between the inward force of gravity and the outward push of pressure. Electron degeneracy pressure allows a white dwarf to not need nuclear reactions to support itself against gravity, because even at 0 Kelvin, electron degeneracy pressure, if you pack your electrons tightly enough, can be sufficient to support the extremely powerful gravity of the white dwarf. And this is the one-dimensional version of that, right? That the electrons are forced to these very high energies because the Pauli exclusion principle won't let them all sit in the ground state. Does that make sense? That's kind of our first pass at explaining all this. So if I want to fill this in then, what do I want to say? This is the key to electron degeneracy pressure. Tightly packed electrons exert much more pressure than they would be expected to if they were an ideal gas. Densely packed electrons exert much more pressure than they would if they were an ideal gas. And it's going to depend on, when I say tightly packed, it's going to depend on how many electrons I pack into this box. So in other words, we'll get to, there's what you call the Fermi energy, which is the highest energy occupied, the energy of the highest energy occupied orbitals, ones that have electrons in them, at T equals 0. And if KT, the thermal energy, is a lot more than the Fermi energy, then it won't be degenerate. Because if you heat up the electrons, they can climb to higher energies in that situation readily. They can easily move to higher energies. But if the Fermi energy is much larger than KT, then almost all the kinetic energy of the electrons is coming from the Pauli exclusion principle rather than from thermal energy. Did you have a question, Isa? Yeah, so the Fermi energy, and I'll be saying it again when we get it. The Fermi energy is the energy of the highest energy occupied orbitals at T equals 0. So in other words, if there are 5 electrons in the box, in the infinite square well, the Fermi energy is E3. If there's only 4, the Fermi energy is E2. If I put in 7, the Fermi energy would become E4, and so on and so forth. So the Fermi energy is the energy of the highest occupied orbitals at T equals 0 when everything's at as low an energy as it can get. And essentially, what we want to do is we want to figure out, see, because this is the ground state, this is T equals 0. If I heat these electrons, they can go up to higher energies. They can occupy higher orbitals. They don't have to be at the lowest energies they can possibly have. Heating the electrons in there corresponds to getting them to occupy higher energy orbitals. Thermal energy is allowing them to occupy higher energy orbitals. They're not in the system ground state. And the comparison to make is the thermal energy, KT, which is what they would typically have as their energies classically, if they were an ideal gas, if the thermal energy is large compared to the Fermi energy, like if the thermal energy corresponded to E sub 50,000 or something, I'm just making that completely up, well, then these things would, then heating the box, you'd have things say way higher energies than just E sub 3 here. And most of the energy is just because it's hot in that situation. But on the other hand, I pack this up to some high occupied orbitals, but the temperature corresponds to something much less than the energy of those much less than the Fermi energy. If the thermal energy is much less than the Fermi energy, then classically you would expect the average energy per particle to be that thermal energy KT. But the quantum mechanics says, no, most of the electrons have way more energy than that because the Pauli exclusion principle has forced them to go way above the thermal energy. Oh, here I am. I'm high thermal energy way down there. I have way more energy than that. Why, I'm going to bang around like crazy and exert all kinds of pressure, you puny thermal energy down there. Why, but if they were an ideal gas, where you eliminate quantum mechanics, they'd have that tiny little energy down there at that temperature and they'd be exerting a lot less pressure. So that's the key. The Pauli exclusion principle is the key to degeneracy pressure, forcing particles to have way more energy because of quantum mechanics than they would have classically. The ideal gas law is a classical expression. The quantum, it comes out of quantum mechanics too, but in the limit that the thermal energy is larger than much larger than the Fermi energy, then you get the ideal gas as an approximation in quantum mechanics, as well as in classical thermodynamics. Okay? It's nice weather up here, by the way, in case you're wondering. I actually feel like it's a little warmer, too. Or maybe it's just because I'm sweating from climbing up here. I don't know. Oh, there's kind of a nice breeze. Oh, there's a breeze here. Oh, this is kind of nice, actually. Yeah. All right.
Don't jump off the table.
I shouldn't jump off the table? Why not? Well, I mean, maybe I've got way too much gravitational potential energy. You don't think I should jump off the table?
Mercy Lee wouldn't like that.
What's the worst that could happen?
You would get scolded by Mercy Lee.
Ah, I see. Why, just because it'll be on the video? You mean if I did this, I might get scolded by her. I can live with that. Okay, yes. Time is it? Okay, so, yeah. All right, what questions do you have? Okay, so that's great. There's our one-dimensional box, but stars are three-dimensional, and they're spherical. Our white dwarfs are. Oh, I'll mention, by the way, too. Right? So remember, let's see. What's the smallest mass that a star can have?
0.8.
Yes, not 0.8. No, it's less than that. It's less than that. 0.08. Well, yeah. So 0.08, about 80 Jupiters, or 8% of the sun's mass. And so, what makes a star a star? A good singing voice. Yeah, but no. Yeah, nuclear fusion in the core, right? Sustained thermonuclear fusion of hydrogen in the core is what makes a star a star. So if you have something that's a bit below 0.08 solar masses, the core never gets to 10 million Kelvin to start the proton-proton chain, and so it never becomes a full-fledged star. If it's got more than 13 Jupiter masses, 1.3% of the sun's mass, why, then it can have a little stellar baby food, right? What's stellar baby food? Deuterium. It can fuse deuterium for a while. All stars fuse deuterium as their baby food, but so if you're between 13 and 8 Jupiter masses, though, they never go off baby food. They just eat a little deuterium for a while, but there's not much of it. It reacts very easily, and so they never undergo sustained fusion. So they're not planets, they're not stars, they are what kind of dwarf? Brown dwarfs. They're brown dwarfs in that situation. What supports the core of a brown dwarf against collapse due to gravity? It's pressure, right? What kind of pressure? Because in a star, right, nuclear fusion is keeping things hot enough to support the core against gravity. In the sun, it's pretty close to being an ideal gas, but it's roughly, as I've seen it, like 10% of the pressures you could kind of attribute to degeneracy pressure in the sun's core. So it's notably off from being an ideal gas, but it's close to being an ideal gas. So what do you think is supporting the core against gravity? There's no nuclear reactions there to keep it hot. What's supporting the core of the brown dwarf against gravitational collapse? What do you think? What's that? It's electron degeneracy pressure, yeah. Electron degeneracy pressure kicks in a brown dwarf before it gets hot enough to fuse hydrogen, and so it goes into a stalemate like a white dwarf does. A brown dwarf has a stalemate in its core between electron degeneracy pressure and gravity. No fusion needed. But if the star is more massive than that, the release of gravitational energy heats the core to the ignition point of hydrogen fusion before it becomes degenerate. And therefore, the fusion reactions prevent the core from turning degenerate as a result of that. But in a brown dwarf, degeneracy pressure kicks in before it gets hot enough for fusion reactions to take place, and degeneracy pressure keeps it stable instead of fusion reactions in that situation. Okay? So, what we have to do now is account for the fact that a star is really three-dimensional. And again, as I said, okay, if we wanted to get fancy, we would treat it as a sphere. We could even say it's, instead of an infinite square well, an infinite sphere well. Even that would be an approximation, but you could kind of be like, okay, well, let's assume that everything's confined inside a sphere and nothing's allowed to go outside the sphere, so you'd make a model where V of R was infinity for R greater than the radius of the star, and 0 inside the star. Even that would be an approximation. It would be a little bit better to do it that way than what we are going to do, but then you would have to use the eigenfunctions for the spherical version of the Schrodinger equation, the spherical coordinates version of the Schrodinger equation, and they're harder to work with. And after all that trouble, you would get results that essentially were exactly the same in the end, it turns out, as you would if you make the simpler assumption that your star is a cube. And so that's what we're going to do. We're going to assume that our white dwarf is a cube that has free electrons in it, because it's hot enough to be ionized, free electrons, and the potential energy will be infinity outside the cube and 0 inside the cube. And so now it'll be that the electrons are in a cubical box instead of a one-dimensional square well. They're in a three-dimensional infinite square well, is what it comes down to. And the idea will be that in each direction, the wave function is a sinusoid where a half-integer number of wavelengths fits in that direction. And the total wave function will simply be a product of one-dimensional infinite square well wave functions in each direction. And I'm going to give you a homework where you joyfully justify this by doing separation of variables on the three-dimensional Schrodinger equation. I can see the delight creeping across your face even now. Have you done that before? Have you done the three-dimensional infinite square well, separate the variables, all this kind of stuff? I don't remember. I might have done it in 280. I don't remember anymore. I probably would do that. But in any case, you'll do it again, because you know what is the key to learning? Repetition, as a matter of fact. Yes. Why, the 13th time you do something, it really starts to sink in, you know? So the cubical star approximation. Here's our star. It's a cubical box. Each side of the box is of length L. V of x, y, z equals infinity outside equals 0 inside. And the box will put coordinates such that the box extends from 0 to L along each dimension. In other words, we put the origin of coordinates in one corner of the box, and so in the x direction, the box extends from 0 to L, and in the y direction from 0 to L, and in the z direction from 0 to L. Result: the energy eigenfunctions, the wave functions that have definite energies, look like this. They're just a product of a one-dimensional wave function for the infinite square well. In other words, you get some overall normalization constant times the sine of n sub x pi x over L times the sine of n sub y pi y over L times the sine of n sub z pi z over L. And so kind of, so it's a product of those. And you kind of say like, okay, well, like, this isn't literally the whole wave function I'm drawing here, but in other words, you can kind of think of it as like an integer number of half wavelengths has to fit in every dimension of the box. And you multiply 3 one-dimensional infinite square well wave functions together, and those are the wave functions inside the box. Questions, comments, observations? It's going to be so cool when we continue this next time. And then we're going to jump into K-space. It's going to be great. We're going to look at spherical shells in K-space. I love this stuff. What's that?
Kathleen space.
Kathleen, that's right. We're going to be in Kathleen space. That's right, yes. Exactly. Oh, I can work with that. I need to think of what to do with that. Yeah, that's right. Yes.
That's why the Boltzmann constant is 4 because it's KB, genetic potential.
Ah, wow. I'm not the only person with a perfect physics name. That's excellent. Wow, I like this. That's great. Nice. That's hot. That's lit or something like that. Right?
Yeah.